Welcome back to my YouTube channel. In the previous lecture, we we have covered the method of matching coefficient in the sequence of the lecture series of the pole placement design. We have started with the pole placement design, in which we have established the concept of why the pole placement design is needed, what the requirement of the pole placement design, how the pole placement design, how the pole placement can be done as per the specification or the design specification given. Also, we have developed the principle of feedback controller design. That is, the dynamics is changed when you consider the state variable as a feedback, and your dynamics will convert to the x dot is equals to ax plus b into r minus r into fr minus kx. That is, your dynamics will convert into the a minus bk plus bf. Okay. So this is your converted dynamics. You can see here a minus bk. Okay, system matrix will becomes like this one. Your system matrix will become like this, and your B matrix is converted to BF. Okay, so you will how you are you then we have started with the method of matching coefficient, and the method of matching coefficient you have already seen the different steps. First of all, you have to check the controllability. Okay, controllability, complete controllability is the necessary sufficient condition in order to design that. Then you have to find the desired, you can say, the characteristic equation based on the desired specification, design specification. Then also you have to develop the characteristic equation with the state feedback gain matrix K. Then you have to compare both the coefficient of like power of the two different characteristic equation. Then you are able to find out the value of K. But there is a limitation of the method of coefficient matching. Uh, so therefore, we have started the new topic, that is the design of feedback controller by transformation of controllable canonical form. We will first try to convert the controllable canonical form, and then we will try to design the feedback controller. So what is the need of why we are going towards the controllable, why we are going toward the conversion, transformation to the controllable canonical form, we will study. So before going to start the lecture, again I am appealing to my students. First of all, if you are not gone through the my previous lectures, so it is my request to go through the previous lectures to in order to build up all the concepts of the modern control system, the basic idea, basic building blocks of that, such as the controllability, observability, and the different types of the homogeneous equation, non-homogeneous equation, solution of the homogeneous, solution of non-homogeneous equation, forcing function and non-forcing function, like that. So if you are not gone through the previous lecture, if you not completed, you established the, you can say, the concept, then you are not able to connect the current lecture. So it is my humble request, first of all you go through the previous lecture, then only you can connect better in better form. Okay, so now I'm going to start the lecture, design of feedback controller by the transformation of controllable canonical form. In this series, first of all, you have to understand the limitation of mathematic matching coefficient method. As you know that in the matching coefficient, we have to draw the characteristic equation. And suppose that if your number of poles become higher, or you can say the system dynamics is higher, then it is very tedious to design, tedious to form the equation or the characteristic equation. And solving the characteristic equation is again a much more complex. Okay, so this is the limitation of the matching coefficient method. The limitation is when your number of poles is increases, or you can say when you consider the higher order system, then the formation of the characteristic equation and solving them is much more intricate, or you can say the complex. So in this case, what is solution? How we can avoid? What is solution for the higher order system? It is very convenient to transform the system into the CCF, controllable canonical form. If the system is higher order system, you simply convert the controllable canonical form to evaluate the feedback gain, that is the K. Okay, you can easily you can find out the value of K. We will see how. The gain matrix is then transformed back. First of all, you have to convert the system matrix into the controllable canonical form. Then controllable canonical form transformed back to the original representation by proper transformation. Let's say we have the third order system, x dot plus x plus bu, x dot is equals to x plus bu, y is equals to cx, and now we have transformed the control into the controllable canonical form. Let's say we have transformed to CCF, okay, by using, you know how we convert. So transformation by using the transformation, you can say simply x dot is equals to pz, right? And you know p is equals to m into m inverse z, okay, m into m inverse z, where m is the controllability matrix of the given state space model. M is nothing but the controllability matrix of given state space model However, mz is mz equal to, you can say, the state model of system in controllable canonical form. Okay, so let's say we have the, and you know that what is the form of the controllable canonical form. You know, if your system is represented in the controllable canonical form, it means for the third order system it is represented like this: 0 1 0 0 0 1, and you know minus a naught minus a1 minus a2 into x1 x2 x3. We already have completed this form, and also we have gone through, this is the important 0 0 1 na? So let's say we have the characteristic equation of, let the characteristic equation will come like s cube plus, since it is a second order system, a2s square plus a1s plus a naught equals to 0. So mz inverse, let's say I'm saying like a1 a2 a1 and a2 1 0 and 1 0 0. This is the mz inverse, let's say, okay. And the z dot, the transformed matrix z, let us consider az bz, sorry, az z plus bz u, y is equals to cz z, right? Y is equals to cz z, where z dot is equals to, you can say, the transformed matrix 0 1 0 0 0 1 minus a0 minus a1 minus a2. This is the transformed matrix, right? z1 z2, you can say z3, okay, plus 0 0 1 into u, or you can simply write like this one: y is equals to, y become, please tell me, c0 c1 c2 into z. So it becomes simply z, okay. So you can also write like z dot is equals to 0 1 0 0 0 1 minus a naught minus a1 minus a2 into z, okay, plus 0 0 1 into u, right? So both are the same. So let your feedback, let the feedback gain, let the feedback matrix be kz, right? And this is becomes, since it's a third order system, so k is 0, k1 k2 we have to consider, right? So now your transformed matrix with, you can say, the system matrix with state feedback converted to the, with the state feedback, you can say the new system matrix. No, new system matrix become, can you tell me, az minus bzkz, right? Az minus bzkz. So what is this? This is 0 1 0 0 0 1 minus a0 minus a1 minus a2, right? minus A2, then 0, 0, 1, and then K0, K1, K2. And when you solve this equation, 100% you will got like this. And that equation is very simple. 0, 1, 0, 0, 0, 1 minus of A0 plus K0, right? Minus of A1 plus K1 and minus of A2 plus K2. So this is the matrix. Okay. So the what we have to done now, we have to find out the eigenvalue or the characteristic equation, and y s minus az minus bz kz. Okay, so the same fundamental I am going to use. Okay, so it will provide you the sq plus a2 plus k2 into s square plus a1 plus k1 into s plus a0 plus k0 equal to 0, right? A0 plus k0 equal to 0. Let us consider from the this equation will develop, this characteristic equation will develop with the help of the, you can say, the state feedback. Okay, this characteristic equation is developed with the state feedback, right? State feedback. Another, the same characteristic equation may be developed with the help of the desired specification, right? Desired specification. So design, you can say, design specification. With the help of design specification, you can draw the desired characteristic equation, right? Characteristic equation. And let's say this is the SQ plus alpha 2s square plus alpha 1s plus alpha naught equal to 0. So what you have to do now? You have to compare, simple. And then by comparing, it will, you find out A2 plus K2 is equals to alpha 2, A1 plus K1 equals to alpha 1, and A0 plus K0 is equals to A0 plus K0 is equals to alpha naught, right? So K2 is equals to alpha 2 minus A2, K1 equals to alpha 1 minus A1, and K0 is equals to alpha naught minus A0. This is the final term. So this will you get Kz, right? It is nothing but the Kz. So Kz is your alpha naught minus A0, alpha 1 minus A1, and alpha 2 minus A2. This is your K0, K1, K2. But it is your Kz, not K. Now you have to convert again, transform into the another form. That is, once again you have to convert into the real form. Okay, this is for the CCF. So the state model, you can say the state model with state feedback, is given by x dot is equals to a minus bk, you know, a minus bk into x plus bf into r. This is the equation for the state feedback in simple form. Okay, and however in the controllable canonical form, the with state feedback, your state model is your state model, you can say state model with state feedback, right? In controllable canonical form is now what? Z dot is equals to az minus bz kz into z plus bz into f into r. This is okay. So you have to again convert into this one, okay, because you have find kz, the value of kz you already have, right? Now you have to convert this one into this form, and then you can find out. So where you can write out where z is equals to p inverse x, because x is equals to nothing but the pz we have already considered. X is equals to pz, so z becomes p inverse x. Az is equals to p inverse ap, and bz is equals to, you know, p inverse b. We already have seen these things into the transformation, and therefore I am repeating go through the previous lecture, okay, and try to understand the basic buildings of the transformation and all other concepts. Okay, so your equation now become, your equation, that is the z dot, this equation. Now let us say, just put z equals to p inverse x. Okay, so z is this one, so z dot becomes p inverse x dot. Okay, and what is the az? Az is equals to p inverse ap. Okay, minus bz equals to p inverse b. Okay, into kz. Okay, and z equals to again p inverse x. Okay, plus this is the p inverse b into f into r. Okay, try to solve this equation. When you solve, you got okay, x dot, because p inverse cancel, so it will give, ap minus bkz p inverse x. Okay, because p inverse cancel. Okay, plus bf into r. And when you solve more something, so it will becomes a minus bkz, right, p inverse okay, into x plus bf into r. Okay, just multiply this p inverse to both. Okay, so it will come like this. So this value is nothing but the k value of k, right? So now your k become, what is k? Your k is, your a minus bk was the previous equation, you can say a minus bk. Okay, so what is the kz here? When you compare this equation, the kz, k becomes your kz into p inverse, kz into p inverse. So once you calculate the kz, you can find out the value of, what? K. You can find out the value of k. K is equals to simple kz into p inverse. Okay, so by finding the value of kz, what is the kz? You can find out the value of kz like this one, okay, minus alpha naught a naught minus alpha 1 a1 alpha 2 a2. So just I'm taking one example so that you can understand it better. So before example, just I am summarizing into the step what you have to take the step in order to apply this, you can say, the transformation controllable canonical form method to find out the value of gain k. So first of all, you have to again check the controllability. Okay, controllability you have to check. I'm not going to detail. Then step 2, characteristic equation, that is s power n plus a n minus 1 s power n minus 1 plus a n minus 2 s power n minus 2 plus dot 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 plus a1 s plus a naught equal to 0. Then step 3 is you have to convert the into the controllable canonical form method, that is the mz, right? Mz, find the controllability matrix mz, find the controllability matrix mz, and this mz is nothing but, how it is given, a1 a2 a3 dot 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 a n minus 1 1, then a2 a3 a4, यहाँ पर हो जाएगा a n minus 1, then 1, then 0, then a3 a4 a5, okay, then 1 0 0, and so on. You can, I think you understood the problem how it is written. So a n minus 1 1 0 0 0 0 1 0 0 up to the Sahara 0, and inverse of inverse of this matrix. Inverse of this matrix is nothing but the MZ. Okay. Next step is the step 4, and this step 4 is you have to find out like this. Step 4. The step 4 is to find M is equals to M into MZ inverse. We already gone through. Step 5, we have to find out the characteristic equation. Characteristic equation based on the designed specification. Designed specification, right? And this is nothing but the Sn plus alpha n minus 1, S to the power n minus 1 plus Sn alpha n minus 2, S power n minus 2 plus dot 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 alpha 1s plus alpha naught equal to 0. This is the equation. Now what is the kz? What is the kz? Kz you can find out based on this both the equation by comparing alpha naught minus a naught, okay, alpha 1 minus a1, alpha 2 minus a2, and so on, alpha n minus 1 minus an minus 1. This is the last step. Last step is k is equals to, when you find out the kz, then k is equals to kz into p inverse, and you can find out the value of k, right? So I am taking one example so that you can understand it better. Okay, so let example is simple. Let's say we have one dynamic continuous time system represented like this: 0 1 minus 6 minus 5 x plus 0 1, and this is a u, okay, and y is equals to 2 1 into x, and the closed loop pole, okay, desired closed loop pole, you can say the desired closed loop pole's location is given, that is s is equals to minus 3 plus minus j4. This is the location of the pole. So you have to, your part is to design you can say again the feedback controller, right? So solution, what is the solution? Simple solution, very simple. First of all you have to check the controllability. B is equals to 0 1 is given, A is given like 0 1 minus 6 minus 5. So this matrix is already given in the already represented in CCF. So there is no need to convert into the CCF now in this form. So AB is equals to, simply you have to check the the controllability and you can proceed. So the M matrix is not equal to 0, that is the BAB, right? BAB, and you can say that the system is completely controllable. So simply step 2, you can design the characteristic equation by S minus A, okay, S minus A, that will give the S minus 1 6 S plus 5 equal to 0, and this gives the S square plus 5S plus 6 equal to 0, and it is represented like S1 S square plus A1S plus A naught equals to 0. Now comes the desired characteristic equation using the design specification. So your designed specification given the pole location should be the minus 3 plus minus j4. Based on this, the characteristic equation desired is equal to S plus 3 whole square plus 16 equal to 0. Okay, and this is nothing but the S square plus 6S plus 25 equal to 0, and this is S square plus alpha 1S plus alpha naught equal to 0, right? So your K naught, that is a K naught, K is equals to alpha naught minus A naught, alpha 1 minus A1, alpha 2 minus A2. Since it is the since it is represented already in the form of the controllable form, so it is with the k is equals to kz. Kz is equal to the k, and since there are only two roots, therefore this will not exist. Only your term will be your only the k is alpha naught minus a naught and alpha 1 minus a1. Okay, so based on this you can find out the 20 minus 6. Okay, and second is 6 minus 5. So your equation is 19 and 1. So the value of k is like this. Okay, so I'm taking one example where not the system dynamics is not represented in the you can say the not in the controllable control form. Okay, so okay, I'm taking one example and then we will finish the video. So let us x dot is equals to -2 1 0 -1. So you can see here this equation is not represented in the form of the controllable control form, and y is equals to given 1 and 3 x. So the question is design a feedback controller to yield a peak overshoot of less than 17% and settling time less than 0.5 seconds. It is very important problem. Such type of problem will asked in the exam. Okay, so the design of feedback controller to yield a peak overshoot of less than 17%. Peak overshoot should be less than 17% and settling time is also less than 0.5 seconds. So this is the specification given. So I am starting with the A matrix. Since A matrix is given like this, -2 1 0 -1, and B matrix is given like 0 1. So AB matrix you can find out the 1 -1, and based on this the M matrix you can find out that is not equal to the 0, since completely controllable, right? We can simply controllable. So the first criteria is passed and we can find out the value of k. We can design the value, right? Okay, now step 2 is very simple. Just we have to find out the characteristic equation. So si minus a equal to 0. So it will give the s plus 2 minus 1 0 s plus 1. Okay, equal to 0. The determinant you can say. So when you solve, you get s square plus 3s plus 2 equal to 0. That is s square plus a1 s plus a not equal to 0. Okay, and here a1 equals to 3 and a naught is equals to 2. Okay, now transformed it. When you transform into the az, you can simply write 0 1 minus a naught minus a, right? So how it will convert? It will convert 0 1 minus a naught means -2. This is the -3. Okay, bz becomes 0 1 0 1. Well, how the z dot is defined now? Z dot is now 0 1 -2 -3 into a z plus 0 1 into z. So this is the transformed into the CCF matrix. Okay. Now AZ BZ will require. AZ BZ will require. So AZ BZ becomes 0 1 -2 -3 and BZ is 0 1. So it will give the 1 -3. Okay. Now calculate the MZ, and MZ is the model matrix, that's the BZ into AZ BZ. Okay. And we already have discussed this thing. So BZ is nothing, 0 1. AZ BZ is given 1 -3. So you can find out the MZ. Okay, not equal to 0, controllable. Yani it means what it means? It means your transformed dynamics is also controllable, right? So MZ inverse you can now find out, that is the 3110 because it required. Okay, So your P matrix is nothing but the m into mz inverse. So you know mz inverse, so you can find out the m matrix is your m matrix was 0, okay, 0 1 1 minus 1 0 1 1 minus 1, and mz matrix is mz inverse matrix is 3 1 1 0, right? So based on this 1 0 2 1, you can find out. Okay, so what is the P inverse now? Because you have to ultimately find out the kz. K is equals to kz P inverse. Okay, kz P inverse. So P inverse you have to you need it. So P inverse you can find out with the help of this equation. Okay, and you can say simply you can transform this 0 minus 2. So this one is the PZ inverse. Okay. Next step is to find out the develop the characteristic equation with the help of the specification. And the specification is nothing but MP is given less than MP should be less than 0.17, right? Okay, so there is a one formula for the MP. Okay, so that zeta is equals to minus of natural log MP divided by root under pi square plus ln mp square. This is a formula just you can apply, and you can find out the value of 0.49, and that is approximately I am doing done 0.5. Okay, now settling time is also given. Settling time is given less than 0.5 second, right? So it is 4 upon zeta omega n is less than 0.5 second. So omega n greater than, you can say, the 4 upon 0.5 into 0.5, that is 16 radian per second. Okay, so considering omega n, because it should be greater than this, so let us consider omega n equals to 17 radian per second. Based on this, you can find out the S equals to minus zeta omega n plus minus j omega n root under 1 minus zeta square. Based on the formula, you can find out the characteristic equation. The characteristic equation becomes s square plus 17s plus 289 equal to 0. That is the s square plus alpha 1s plus alpha naught equal to 0. So here you can now find out the value of kz. Based on this, the problem becomes very simple. Alpha naught minus a naught, alpha 1 minus a1, and alpha 2 minus a2. Okay, so your this is the 289 minus 2, right? Then 17 minus 3, and then, okay, since it is a second order system now, and therefore we are not going to consider this one. Okay, so your problem becomes, your answer becomes 287 and 14. So this is the kz. Now you can convert the k, that by formula applying kz into P inverse, and it is nothing but the 287 and 14, and your P inverse is nothing but 1 0 minus 2 1. With the help of this equation, you can solve the equation 2 5 9 and 14. So this is the ultimate answer. Okay, so in the next lecture we will try to understand the Ackermann formula for the controller design. Okay, so still, thank you very much.